Sorry for interruption. There is some technical issue of internet. Okay, now we would continue the same. So, am I audible? Am I audible to you?
Yes, sir.
Okay, thank you. So, we are discussing that we are using actually the two transistors that is symmetrical to each other, and in this particular diagram, if you have to be see, the transistor Q1 and Q2 are symmetrical, and both emitter terminal would be come here and joined here. So that is the collector terminal of the Q3. So whatever the value of IC3 that is equivalent to IE3, it would be a combination of the current that is flowing through this Q1 and Q2. So you can consider IE1 and IE2 both would be equal, and it would be half of the current IC3. Okay, so same thing I have mentioned here. So IE1 is equal to IE2 is equal to IC3 upon 2. So that is, we have put up on the equation of the IC3, that is VE minus R2 upon R1 plus R2 VE upon 2 RE. Okay, so this is the equation you can consider as a 5 number. So the collector current IC3 in the transistor Q3 is become fixed. Why it would become fixed? Because no signal is injected into either the emitter or base of transistor Q3. So in the previous case, there is that we have considered a condition that we have to be increase the value of RE to make the IE constant. That would be not acceptable because it would be decrease the value of IE. But when you are using this configuration, means constant current biasing, so you would be find out that no extra signal that would be injected to the base or either the emitter of this transistor, means IC3 would be remains constant throughout the operation. Okay, so this is one of the solution for providing the constant current. Okay, but beside this supplying constant emitter current, the constant current bias also provides very high source resistance. This is also one of the advantage of this. Therefore, all the performance equations obtained for differential amplifier using emitter biased are also valid. Now we have to be learn what are the practical issues could become with this configuration also. So one of the issue is thermal stability. So we have to be now learn the new configuration, that is constant current biasing with the thermal stability. So as we have seen in the expression of IE, there is a term VBE3 is there. Okay, and this VBE3 is temperature dependent term. If the temperature changes, voltage between base to emitter would be also change, and if VB is changed, means the current IE would also change. And to improve the thermal stability, what we have done the modification, we have connected one diode in series with the resistance R1. You can see here we have connected the diode. The voltage across diode is VD in series with the R1 in the voltage division network of Q3. So here we would only consider the area where Q3 would be connected. We have not shown in the diagram the rest of the part of the differential amplifier. Now this diode would be helped to hold the current IE3 constant even though the temperature changed. Okay, so for thermal stability we have to be connect this diode in series with the R1. So see how this would be function. So in this case we have to be first do the mathematical analysis to understand this function of the thermal stability. So apply KVL around the base circuit of the transistor Q3. So this is the base circuitry of Q3. So around this base circuitry, you have to be apply the KVL. Okay. So we have to be apply the KVL here. So either you have to be apply in clockwise manner or anti-clockwise. It depends upon you. Okay. Suppose we have taken this kind of clockwise. Okay. So for this purpose, we have to be, this is the base of Q3. So around this base, we have to apply this KVL. So you can take as VBE3, it is plus to minus, means drop in potential. It would be considered as a positive here. Then again, second drop in potential, that is IE3 R3. Again, it has been taken as a positive. Okay. Now we have to be through this minus VE, we would be come to this R1. So it is again plus minus plus minus. So here we have the rise in potential. So we would be considering it as a negative, because all drop in potential we have taken as a positive. So rise in potential would be considered as a negative here. Okay. So first of all, we have to take a negative sign. And what is the voltage rise across this R1? So what is the voltage across this R1? It is not known till, because the current is not defined here. So for that purpose, we can define the current. Okay. So the current across it is what? The current is whatever the current flowing across R1, that is the voltage across R1. So voltage across R1 is what? It is connected, one end is connected to the negative supply. It would be considered as we have considered all the rise in potential as a negative and drop in potential as a positive. So V would be considered as a positive because it is negative voltage source, minus this voltage VD upon R1 plus R2, because it is a voltage division network. Okay. So we have to be considered the total voltage. That also shown here in this particular networking also. We have separately shown this voltage division network to understood the concept of this. So it would be become voltage across R1 is VEE minus VD upon R1 plus R2. And the voltage drop is, this is the current actually, multiply with the R1. Then another voltage in this path is rise in potential across diode. So it would be again taken as a negative, minus VD equal to 0. So when you have to be take this on the other hand of the equal to sign, so it would be become VEE minus VD R1 upon R1 plus R2 plus VD is equal to VBE plus IE R2. So from this equation, we can easily derive the equation of IE3. Okay. So when you are going to derive the equation IE3, it is very simple. We have to be just take VBE3 on the other hand of the equal to sign. So it would become minus here and divide by the RE. So this would be become the equation for IE. Okay. Now it would further simplify, because still it is a quantity, that is VBE in this equation, that would be affected by the temperature. So we have to be adjust the value of R1 and R2 in such a way that R2 upon R1 plus R2 into VD would be equal to the VBE3. To cancel the effect of VBE3, we would be adjust the value of R1 and R2 in such a way that R2 upon R1 plus R2 into VD would be equal to the VBE3. So what would be the effect of this? This would be cancel out. This two term would be become cancel out. So only the term would be remaining is IE3 is equal to VEE into R1 plus R2 into 1 upon RE. Okay, so it would become independent of the VBE3, and if it would become the independent of the VBE3, means it will become independent of the temperature. So therefore, the current IE3 is constant and it would become independent of the temperature because of added diode D. Okay, but still this diode would be cancel out this VBE3, because we know that VBE3 would be decreases approximately twice of millivolt per degree Celsius. Per degree rise in temperature, VBE would be decreased by the 2 millivolt. That's why we have connected a diode here to balancing this temperature effect. Okay, so in this way we have seen that diode would be make the emitter current independent of the temperature. Now the diode has the same temperature dependence, hence these two variations, means the temperature effect on the VBE and the temperature effect on the diode, would be cancel each other. Okay, and IE3 would become independent of the temperature. But sometimes what happens, maybe because of the construction of the diode and the transistor, VD voltage drop across the diode would be not approximately same. It may be possible because of the manufacturing limitations that VD would be not equivalent to the VBE3. So at that condition, this remedy, means connecting one diode, would be failed. So to counter this problem, we can also connect two diodes. Instead of one diode, you can connect two diodes in series to compensate the change in the voltage due to the temperature across the base to emitter terminal. Okay, so this is another way that you can handle this. So we have seen that how to control the variation of the voltage, and IE3 with respect to temperature has been be sorted out with connecting one diode in series with the R1. Now the another method that you can use, that is constant current bias with the Zener diode. Okay, so this is the configuration. Everyone please note it down. Instead of R1 and diode, we have simply it is replaced by this Zener diode, and we know that it would be function in the reverse bias conditions. That's why the polarity of the diode would be connected in this way. This is cathode is connected to the base and anode is connected to the VEE. All of you please start to fill up the attendance because time is 1 minute left only. So we would be discuss this configuration in the next lecture. This Saturday, I think there is a one lecture of the data structure. After that you are free. Yes or no?
Yes, sir.
Please reply me. So in this Saturday, we would be plan the lecture because we have not conducted the lecture on Monday, so we will be conducted on this Saturday. Okay, maybe 11:50 or 10:40. Okay, thank you all of you.